Hello, Flat Earth researchers, debaters and debunkers. Again, we're looking at how the globe was constructed mathematically as a model from what is originally a level Earth. And that's simply done by choosing a unit of measurement, i.e. nautical miles, or nm, that is the equivalent to 90 degrees. And so when we've converted distance into degrees, we then have a way that we can illustrate what is a level Earth as a globe. And then we also have degrees in terms of the way we look at time as a circle, a 360 degree circle that comprises minutes and seconds, and we get 360 degrees. So ultimately the globe is constructed in a way that brings together units of measurement or units of calculation that can be illustrated as a globe. So we'll come back to this in a second, but just to start with, to illustrate the point, what we can have is a vast level Earth of an infinite plane. But here I put a North Pole and I put a South Pole. We can start with the North Pole because that's a reference point. We have our Polaris as a reference point for our North Pole, don't we? Okay, so that's a good place to start. And the South Pole is just a certain distance from that. So what you can do is you get in this case I'm using a cube template, okay, and I'm putting it over this portion of what would otherwise be an infinite plane. Sorry, it's wet, it's been raining. But so you have all this land and sea outside of this area. That's not there. But if this was transparent, we would have this on top of the land masses and the sea beneath it. Okay, so that's our overlay. This is a cube just because it's easier, but you get the idea. It's a cube template. We've got a North Pole here and a South Pole that's a certain distance. It's basically the same distance again from the North Pole to the equator, which would be somewhere around here, and then that same distance again down to the South Pole. So this could well be Antarctica. You look at maps and you see Antarctica as a continent. There's no reason to disbelieve that it exists. It could well exist. The form and the shape it really takes might be up for debate, who knows, but you can certainly have it included on your map and it would still just be from a flat Earth. And so you end up with a cube Earth, a three-dimensional cube Earth as an abstract mathematical model, which of course you can turn into a physical model, but it all comes from this here being one long or one expanse of level Earth. Okay, so hopefully this will make it clear how you actually get the 5,400 nautical miles and turn those into degrees. Okay, so what you have here is if you're looking, this is a side-on view, an orthographic side-on view of a level Earth, or the boundaries of a level Earth that we have. Okay, and this doesn't have to be measured to its extremities. We can just start off from here, the North Pole, okay, and then get as far as the equator. Okay, so what we have here is the North Pole is referred to as 90 degrees, because if you were under the North Pole, you'd be looking up 90 degrees relative to your horizontal along your level Earth. Okay, and that horizontal distance to the equator is 5,400 nautical miles. So in this case, 5,400 nautical miles from the North Pole to the equator across a level Earth is considered as 90 degrees. Okay, and so this would be going off to say the east, and this would be going off to the west. All right. Then you've got your equator and beyond. So all you do is just add another 5,400 nautical miles, or another 90 degrees. Okay. So you've got 90, 90, 90, and it all adds up to 360 degrees. And so if you just do 5,400 nautical miles times by 4, I think you're going to get something in the region of 21,600 nautical miles. Happens to be the circumference of the Earth as far as nautical navigation goes. Okay, so just looking for that. All right. Let's see how this all works. So the 90 degrees to the 0 degrees is the angle of altitude that we see Polaris. So if we just take this section here, this North Pole to the equator here, 5,400 nautical miles, okay, and that is our 90 degrees, okay. You can put a triangle there, or you can put it as a round edge there, okay. It's a level surface. And so here we have Polaris at 90 degrees, okay? We are here at the North Pole, so here is here, okay? The North Pole, all right? And then these degrees that we see Polaris at, depending on the distance from Polaris, are the actual latitudes on the Earth. So there's certain countries at 80 degrees latitude, and that's because to line up with Polaris is an 80-degree angle. Okay, and then you get further away from the North Pole, and here at latitude 70 is where the Polaris appears at 70 degrees. Okay. And then 60. I'll just show you on here this little angle meter. The angles, so we're basically drawn in the actual angle. Okay. All right, there's 70 degrees. Get further away, and it's coming down to 60. Okay. Get further away, and it comes down to 50. All right. Get further away. So what's happening is, of course, these lines are not going to the same location. This is the mistake that is made when people say, oh, it's impossible to have the angles that you see Polaris on a level Earth, because what they will do is they'll draw your level Earth, they'll draw Polaris up here, and then all those angles, they'll actually keep Polaris fixed. And so they'll draw their angles like this, okay, and they'll say, well, it's impossible, when you do it to scale, to get to 0 degrees. It's impossible to draw a line that would be 0 degrees to Polaris. Well, of course, what you're not doing is you're not actually representing how Polaris is seen in the eyes of the observer when they're looking through a sextant or something like that. Okay, so when we actually represent, when we just draw it like this, you can see that Polaris does appear lower in the sky, just as it does as you get further and further away from it. And what you end up with, if you do, you can try this yourself. You know, get one of those rulers for nautical miles, or just space them at an equal distance apart. Draw the angles in, draw them in units of 5 or whatever you like, and what you end up with is a nice curve here. Here is the curve, okay? Not here. So this curvature of an Earth is constructed from this, and it's really just these 4, well, it's 2 hemispheres, isn't it? You've got your 90 degrees there. You just draw that with a different one, okay? 90 degrees there, 90 degrees there, and you have a hemisphere. And then these lines here, going from the equator to the South Pole, are simply another 90 degrees, because we've already established that 5,400 nautical miles is the same as 90 degrees. So really what we have is a straight line that is then folded around into this globe-like illustration, and we're able to do it because we're talking about degrees. So let's just clarify how those degrees are done, yeah? Because it's all about dividing things up. Just grab this to make sure that we're on the right track. Okay, so again, we're talking about it's all about minutes and degrees, minutes of degrees, okay? And for example, 1 minute, now this isn't a minute of time, it's a minute that's a fraction of a degree, okay, is equal to 1 nautical mile, okay? Now, if you put 60 minutes, that's equal to 1 degree of declination, or 1 degree difference here, okay, between 0 and 90, okay? So 60 minutes make up 1 degree. So that means that 1 degree is also equal to 60 nautical miles, yeah? Okay, 60 nautical miles. So, given that we have 90 degrees every time we do a measurement, okay, from the North Pole to the equator, and 1 degree is 60 nautical miles, what we do is we multiply our 60 nautical miles by 90 degrees, and that will give us our distance from the North Pole to the equator as being 5,400 nautical miles. Yeah? Okay. Does that make sense? Yeah? Now, that's why we talk about knots. Okay? And you go at a speed of knots on the sea or in the air. Okay? Sorry, this is getting a bit cluttered, but 1 knot is equal to, just check this for sure, 1 nautical mile per hour. 1 nautical mile per hour. Okay, 1 knot is equal to 1 nautical mile per hour. Okay, so that's going to equal 1 minute of degrees per hour. 1 knot is going to be 1 minute of degrees per hour. All right, so that means that 60 knots per hour is going to give you, for example, 60 knots per hour is going to give you 1 degree per hour. In an hour you'll do 1 degree, and that will be the same as 60 nautical miles in 1 hour. Yeah? Okay, so they're all correlated. They're all related. The knots, that's why we have knots, because it relates to the distance you travel and the time you travel to get these degrees, in line with these degrees. Okay? So, if that's clear, we can go on to talk about distances again and how to work those out. All right, keeping in mind that 1 degree is 60 nautical miles, okay? So we've got this distance here. Any distance beyond the equator, we don't need to see Polaris anymore. We've already got our equation as 1 degree of declination, or it doesn't even have to be declination, it's just 1 degree is the same as 60 nautical miles. So you can just have this, and that's where that will get turned into a globe. So when you're actually navigating, what happens is, let's just go for this one for example, say you're measurement, you've measured your angle to Polaris as being 40 degrees. What that means is that angle there, okay, all right, and then you look at what's left to get to your 90. You create a 90-degree angle, okay, along your flat plane, perpendicular to your flat plane horizon. 40 degrees is the angle of altitude that we see from the horizon, up from the horizon to Polaris, 40 degrees. What's left over to get to 90? 50, 60, 70, 80, 90. We've got another 50 degrees left over here. So again, the distance between us here at 40 degrees and the North Pole is simply a case of doing the remaining 50 degrees multiplied by 60 nautical miles. And where's my 50 times 60 equals 3,000 miles. Okay, 3,000 nautical miles. All right, so right here we know that our distance to the North Pole is 3,000 miles. Yeah, and so it goes on. You've got your points at which you want to have another 90 degrees, and that takes you, so you can see that how this is then folded into a globe, just as we took this and folded it into, a cube. All right, so this length here would be like this length here, and we just folding here. Okay, it's a little bit out of sync, but you get the idea. Okay, all right, yeah, so there's a lot of land we might see, we might not see, we might not know about because it's not on our maps. It was never included. Okay, and what we have here is just a bunch of mathemagic distances turned into degrees that will eventually give us a 360 degree circle, because of course 90 times 4 gives you 360 degrees. Yeah, you've got your hemisphere, 180 and another 180, two hemispheres gives you 360 degrees. Yeah, really simple stuff. So when you take the actual observations and you put them like that onto our level Earth, you can see that we are seeing the results of perspective and how perspective has become the imaginary curve. You can use trigonometry or geometry to create this imaginary curve. Of course, it gets a little bit more complex when you go to talk about other distances and directions and headings, and we'll cover that later. But what's really important to know now is how these degrees have been derived from distances on a level Earth. And it's only by doing that that you're able to turn it into a globe. So don't let anyone tell you that the globe came first. The level Earth came first, and the observations of Polaris at various distances along the level Earth. Okay, these are all latitude lines, and so if you're in a place that's on a certain latitude line, that's the degrees that you'll see Polaris from. Nothing changes. Nothing changes except the way that you interpret these things, these measurements, okay? And to interpret these measurements with Polaris as a fixed star doesn't work, because in our vision it's not fixed. It does appear to come down to the horizon, okay? And actually what you end up being left with is once you go, if you get to this is where the 23.4 degrees is hidden, okay? Doing it this way ends up with you getting a little bit further away, that it equates to 23.4 degrees, okay? But we'll have a look at that a little bit later. Hopefully that's enough for now to understand that you start off with a level plane, get your distances, turn them into degrees, and use a unit of calculation or measurement that matches those degrees. And voila, you have an imaginary globe Earth. Thank you very much.